Okie doke. The last video, or possibly two, on the DHSS model effectively. So at the end of the previous video we said when we look at the data it seems that, so what did the data say? The data said that Y and R seem to have this trend, whereas WR has that trend here. And the model that fitted that data was the one with abundant resources, costly to extract. So that's kind of cool. That's suggesting that this model is telling us something interesting. But on the other hand, we know that resources aren't that abundant. In this model we assume they're infinite. They'll never run out. But if we keep exponentially increasing the quantity of resources we extract, clearly they will run out. So perhaps this is because it's a long time till they run out. So we see this for the time being, but in the future we're going to have to change. Maybe, like limits to growth, we'll go over a cliff, or maybe we'll gradually adapt. Okay. Can we get our heads around that? Can we model that and understand better what's going on, when we have to change, etc. And have a model which we can apply to empirical cases and actually make predictions. So just before we go on, perhaps, are resources abundant? Like, does this make sense? Well, when we look at things like iron ore extraction, even oil extraction, coal extraction, aluminium, you name it, there's an incredible amount out there. Okay, there are phenomenal amounts of resources out there, with the exception possibly of oil. I mean, the thing is, the Earth's crust is a bloody big place, right? I mean, it's huge. The Earth is huge. The Earth's crust, I can't remember how thick we define it as, but it's huge. I mean, it's just huge. There's so much stuff out there. We're just scratching the surface for most resources. Even for like the rare earths and so on. Sure, they're expensive, tricky to find and so on. But when we think about the total quantity that's out there and the amount we're extracting at the moment, it's small. Okay. So this seems like a reasonable starting point, that maybe this fits, because at the moment it's as if resources are abundant, but clearly in the long run we're going to hit some limits. So how can we model that? Can we model it better than just saying we're going to fly over the cliff? We can. Okay. By the way, when would we fly over the cliff if we carried on like we are doing now? Limits to growth people, they said in middle of, from today in about 30 years. I say, well, if you take the resource rate of total mass of extraction of stuff from the Earth's crust and assume it keeps growing, I think it was 3% a year I calculated on, forever. How does that look? It turns out that in 700 years' time we're digging up the entire Earth's crust every year. Okay, so clearly that upward trend in the mass of material we're digging up has to flatten out a lot earlier than 700 years' time. So that gives you some kind of perspective. Okay, so how do we set about building an economic model? I'm not going to talk about the limits to growth model, which is horrible. I think I say a bit about it in the book. How do we set about building a proper economic model of what's going on? page 13. And this is based on an article that I published in a very good journal in 2016. Consider the picture below, slide 13. Try to identify as many such factors as you can. There's something missing here, isn't there? Never mind. Factors affecting the costs of resource extraction. And are they going to cause costs to fall or rise? And what have we got in the picture? We've got someone digging up resources out of the ground, haven't we? So, the wage is going to cause costs per unit of resource to rise, isn't it? And if we take this literally, if we call this D, the depth is going to cause costs to rise. So if over time we dig up more resources, we end up having to dig deeper, and that gets more costly. But the technology, the productivity of this worker plus her capital, if that goes up, all else equal, for the same wage for the worker plus implicitly capital, if that is the same but this goes up, then costs are going to fall, aren't they? And then the point about the two pictures, one with a narrow tube of resources, the other with a broad one, is that if the tube is broad, for a given extraction rate, D will tend to fall, increase more slowly, right? So if this is diamonds, if you extract a ton of diamonds from the global crust, the next ton is going to be a lot harder to find. But if it's iron ore, you extract a ton of iron ore, you're just scratching the surface. You're not even scratching the surface. You're just, I don't know what. There's a phenomenal amount of iron ore out there. Okay, so how do we capture this in a model? We do it like this. You don't want to watch me drawing for ages. I'm going to pause this and draw. Okay, let me talk you through this model then. So it's very similar to the model with abundant resources costly to extract. But the first thing to notice is we've eliminated capital, because it turns out we're interested in balanced growth paths. On the balanced growth paths, capital always tracks growth, so it basically doesn't play any role. Okay, so we can think of labour capital together, and we basically don't lose anything for the models, these long run models that we're interested in. So just makes things a bit simpler. Okay, we could put it in there, everything would work out the same, but it would, the math would be horrible. Okay, so we've dropped capital. But instead of having final goods used as the extraction input, we have labour. And that's just, again, we could have done it with final goods. I think it's a bit messier. Again, the results will be the same. I'm not even 100% sure what I did in the paper, whether it was final goods or labour. But here I've chosen labour anyway. So we have labour Lx going down the mine. We have the breadth of the resource stock, phi, and we have the depth, d. And we have a sort of extraction productivity difficulty factor, AD, which is e raised to the power of d. Okay. It just turns out that this gives us a nice convenient forms. When we try to imply this empirically, we can relax this. It's not like we have to assume that resources actually look like this when we're applying this empirically. But for the theory calculations, this is simplest. and then we assume that the labour productivities AY and AX both grow at G exogenously. So then, for a given amount of labour, Lx, if AX is going up, you'll get more resources out. But if AD is going up at the same rate, that will cancel and you'll get the same amount out. Right. Okay. So what's going to happen in this model? Well, first we need to do some basic math and say, well, what is D dot? How is D going to change over time? Let me see. Let me just pause this for a sec. Yeah, so this is basically, we just write this down from intuition. D dot is X, the extraction rate, divided by phi, the breadth or the surface area, if you like, of this column. So this is just like follows by definition, basically. If you've got a narrow column, or if your column is like 1 unit wide, then D dot, the rate of increase in D, is equal to X. So if you're extracting a unit per period, D will increase by 1 unit per period, if this is 1 unit wide. But if you're extracting a unit per period and this is 5 units wide, D will go up by 1 over phi, won't it? So D dot is X over phi. Then, given that, how does AD change? AD dot, that's dAd by dt. What's that? It's AD of t is ED of t. So that's dAd by dd, dd by dt. We divide this up. How does AD change with time? It depends on how AD changes with D and how D changes with T. And how AD changes with D, dAd by dd is just, the differential of this is just e to the d, isn't it? Which is AD. So that's AD, and dd by dt, that's D dot. So AD dot is AD D dot, which means that AD dot over AD is D dot. So that's kind of nice. Okay. Which is equal to X over phi. Okay. So we're now in a position to start solving this model. But we're just going to focus on 3 very simple extreme cases. In the paper I solve, it's super tricky actually, optimal control theory to work out for the whole path. But here we're going to look at 3 extreme cases. And the first of these, and I think I'm going to go through the first of these in this video, page 15, assume a primitive economy in which AY is very small. What happens? Okay. So if AY is very small, then, and that means, I never said that, but AX is also going to be small. Okay. So Y is going to be small and X is going to be small. Okay. If X is small, what can we say about D dot? That means D dot is small. And we're saying really small. Yeah, we're simplifying. We're saying it's super primitive economy. Y is small. We've got very little production. X is small. We've got very little extraction. D dot is small. We're scratching the surface of the resource stock. which means that AD dot over AD is small. We can treat AD as constant. Okay? Think of the Stone Age, or the beginning of the Iron Age, whenever that is, a couple of 3,000 years ago. We're starting to use iron. What effect, as we extract little lumps of iron ore from places, what effect is that having on the global stocks of iron ore in the crust? Not much, right? I mean, to say you were scratching the surface would be an exaggeration. Yeah. So we can treat the depth as constant. We can treat the resource stock as abundant. The exhaustion is not an issue at this point. We can treat AD as constant. Then we have X is AX, LX. Guess what? When we work this through, we just get exactly this economy. Admittedly, well, I've simplified by removing capital accumulation, and instead of having X and a fixed productivity, I've got LX and an increasing productivity. But remember, LX will stay the same in balanced growth. AX will grow, but WL, the wage to labor, will grow. You have to pay the same wage in both sectors. Yeah? So labor productivity goes up, the wage in both sectors goes up, the cost per unit of extraction will stay the same, the resource price will stay the same. Let's go to slide 16 and see what it says. X is small, D and AD are constant, which means that, let's do the math. If AD is constant, then in balanced growth, then the L's will also be constant, and we can say that X dot over X is G. And if X dot over X is G, then remembering our old results from those simple economies, this is growing at G, this is growing at G, this is constant, Y will grow at G. What else have we got? Expenditure on the resource will be alpha Y. This follows from the Cobb-Douglas that you will always spend a share alpha of your costs will go to paying for the resource, and a share 1 minus alpha will go to labor. And since X is increasing at the same rate as Y, that means that WX must be constant. So this is just like the abundant resource costly to extract case, which of course you'd expect because we've got an abundant resource costly to extract here. Okay, what might a reasonable value for alpha be? Have a think about that. I haven't put that in the questions. I'll try to remember to put it into the study questions. What might a reasonable value for alpha be if we're trying to match this to real economies? Okay. I'm going to stop this video there and we're going to go on to the other two cases.